Today we will discuss protection mechanism, and that too the electrochemical ways to protect metals or alloys in a corrosive medium. So, today we will start protection mechanism, and that too electrochemical protection mechanism, and two things are coming under this subject. One is cathodic protection, the another one is anodic protection. So, before going to this electrochemical protection mechanism, so let us first see how many ways one metallic object or alloy object or structure can be protected from corrosion. So, in fact, complete protection from corrosion is economically not preferred. So, we will try to have some sort of mechanism where we can control the corrosion. Rather, the corrosion rate can be reduced to a great extent, so that the metallic structure or the alloy structure can be used for a much longer period. So, let us first see how many ways we can have the corrosion protection. So, this is different methods of corrosion protection. Now, you can have different protection mechanism. There are 5 broad groups. One is design equipment, second thing is change of metal, then change of environment, then change of metal electrode potential or change of electrode potential, and then you have use of coating. Now, our thing, this electrochemical protection mechanism is falling under this category. So, here we have two ways. One is cathodic protection, and second one is anodic protection. Now, we will in this particular lecture we will discuss in detail about these two methods, but before that let us see how many ways we can what are the subsections of these different main sections. Change of metal, it can have 4 different subsections. One is change of composition, second one is change of microstructure, for example, change of composition. One example is, let us say you are considering, let us say you have the corrosion of intergranular corrosion of stainless steel, 18H stainless steel, austenitic stainless steel. There if you reduce the carbon content below 0.03% weight percent, then we can definitely avoid the intergranular corrosion of austenitic stainless steel, which is having 18 weight percent of chromium and 8 weight percent of nickel. So, change in composition can lead to have a better protection against the corrosion. Change of microstructure, austenitic, ferritic, both have a different microstructural level. Okay, so, you can also have a different, for example, if you have a pearlitic structure, if you have medium, let us say mild steel with a carbon content of 0.4, where you have a mixture of ferrite and pearlite. So, if you reduce the pearlite content, then we are going to increase the corrosion resistance. So, change in microstructure also helps. And third one is elimination of stress. Let us say your material, the material under operation is having residual stress into it inside the material, then the most possible susceptibility, most possible cause of failure would be stress corrosion cracking. So, if we can remove that internal stress, then we can avoid the stress corrosion cracking. So, again a sort of protection. And then you have introduction of surface compressive stress. So, this is one more way. So, if we introduce surface compressive stress, then it would have inherent resistance against fatigue. So, there is one more ways, one more way the material can fail if there is some tensile component, that is the fatigue corrosion. So, if we have this surface compressive stress, we can reduce the tensile component part. So, we can have little extra protection against the fatigue corrosion. Fatigue corrosion or fatigue corrosion failure. Now, coming to this change of environment, it has also different parts. So, let me put this change of environment singular here, change of So, by changing the environment where the material or the alloy system or the structure is exposed to, if we can change that environment by some external means, we can avoid corrosion related problem. So, there are different subsections. One is removal of corrosion. We have seen that in case of zinc corrosion in HCl, if we have impurity, then the corrosion rate of zinc increases. So, if you can get rid of the impurity. Another case is if you can get rid of oxygen, dissolve oxygen. If you do not have dissolved oxygen, then the corrosion rate automatically goes down. So, like that, so it can be either removal, oxygen removal, second is moisture removal, or it can be purification. Let us say that HCl does not contain any ferric ion, then the corrosion rate of zinc will reduce. And then you can also have one more way. If you can remove the salt purification, in the under this purification you can have salt removal. So, if you can get rid of ferric chloride percentage or weight per ferric chloride presence in HCl, so zinc corrosion rate will reduce. And moisture, let us say in a dry place or in wet place, wherever you have moisture. So, once you have moisture, if you have oxygen, then this reaction can happen. And this is a cathodic reaction. Once you have a cathodic reaction, so you have to supply electron for this cathodic reaction. So, electron will come from the corrosion of the metal object. So, if you do not have moisture, even if you have oxygen, then the corrosion problem, aqueous corrosion problem can be stopped, can be greatly avoided. So, these are three ways where you can have a removal of corrosive. Second case is inhibitors. Inhibitors, some external agent can be added into the medium which will take care of those corrosives, and this part will be taken. I will just consider this change of electrode potential part, the other parts will be taken care of by Dr. Choudhury. So, this is inhibitors. In the inhibitor part you can have one is chemical pacivator, then you can have absorption pacivator, adsorption. Adsorption pacivator. You can also have film forming pacivator, even you can have vapor phase pacivator. So, four ways you can have some external inhibitors which can introduce passivation on the material, so that the corrosion rate will be reduced. Then you have change in operating variables. What are those? Operating variables, let us say temperature. In general, if you reduce the temperature, if temperature is reduced, corrosion rate will be reduced. Then second case is pH. As we have seen in case of Pourbaix's diagram, if pH is increased and if potential also can be taken to the level of region, to the level of formation of passive film, then increasing pH generally helps. So, this is one, and then you have velocity of liquid. So, we have also seen from mixed potential theory that if we increase the velocity, generally the corrosion rate increases, but in case of passive, active passive metal, after some critical velocity the corrosion rate suddenly drops. Now, these are the three ways. So, this is a change of environment. Then you have use of coating. So, use of coating, it can have two subsections. One is, and the coating means application of some external agent or external film on the metallic object to have protection from corrosives, from corrosion. So, one is metallic coating, then it can also have two subcategory. One is cathodic coating and another one is anodic coating. So, one case it will act as cathodic coating and another case it will act as anodic coating. And then you have non-metallic coating. Non-metallic coating, there you have different subcategories. One is vitreous coating. Vitreous coating is a sort of amorphous coating on the material, and since amorphous material does not have any grain boundary, so it gives automatic protection against corrosion, because the grain boundary regions are the regions which are vulnerable to corrosion attack. Then you have cement, then you have paints, organic paints. In case of car bodies, we generally put organic paints. Then you have chemical conversion. So, this is the entire picture of corrosion protection methods. So, now let us concentrate on this particular part. Will concentrate. So, let us start with the cathodic protection. So, let us start with cathodic protection. And this electrochemical protection mechanism is nothing but the change of electrochemical electrode potential. So, in case of cathodic protection, before we start, let us see what is cathodic reaction. So, let us say this is my cathodic reaction. Mn plus ion is taking any numbers of electrons and going to M. This is the cathodic reaction. Now, in this reaction, let us say if we supply electron, and before supplying, let us say this has reached equilibrium. Let us say this is the equilibrium reaction, where cathodic reaction is the forward reaction and anodic reaction is the backward reaction, and that is basically let us say T and P, constant temperature and pressure, this reaction is taking place. So, without changing the temperature and pressure, if we supply extra electron from outside to this system, to the left hand side of this reaction, so equilibrium will be broken and it will reach to a different equilibrium state. So, in order to reach that, since we have extra electron, so this forward reaction will happen at much faster rate. So, if forward reaction happens, it means that the metal ion has higher tendency to go into the metallic elemental metal. So, when this elemental metal formation is taking place, it means that the reverse reaction is taking place at a much slower rate, and this is faster rate, this forward reaction, which is the cathodic reaction. So, that means if we can supply electron from external source to this left hand side, we see that there is a sort of deposition rather than corrosion or dissolution. So, this is exactly the basis of cathodic protection. The basis of cathodic protection is, one is supplying electron supply electron from external source. And supply electron from external source means, if you consider with respect to current, because we can supply electron by applying the negative current. And here if you consider this way is basically I A, small I A, which is anodic current density, and this reaction is basically I C. So, that means if we can supply negative current to this system, so I will have more and more cathodic reaction and anodic reaction, which is basically nothing but the corrosion reaction reduce, the rate of that reaction will be reduced to a great extent. So, this is supply of electron or negative current. Supply of negative current to the system or supply of IC or cathodic current. This small IC is basically cathodic current density. We are supplying some cathodic current and which is divided by the area of the cathode region. That means, it is basically converting to cathodic current density. Now, another thing is, if you see the protection principle, we are actually trying to make the metal object which is to be protected a cathode. So, making the metal object a cathode. So, if you have a metal which is to be protected, it has to be made cathode. So, how can we make cathode? So, one way is we can connect it to a negative terminal of a power source, DC power source, and the other positive terminal is connected to an auxiliary electrode, AU or AE. AE means auxiliary electrode. So, since we have connected it to the cathode part and we are concerned with the protection of this metallic object M. So, since we have connected to cathode part, so it has become cathode. So, once it has become cathode, the cathodic reaction will occur on this surface and anodic reaction will occur on this surface. So, the cathodic reaction, if cathodic reaction happens on a particular object, metallic object, so that part is cathodically protected. So, this is cathodically protected because of cathodic reaction on cathode surface. So, now you see whether we are satisfying these two things or not. First thing is supplying electron from external source, and in fact, we are supplying, we have connected it to negative terminal. So, the current, positive current, which is I, is actually flowing from positive to negative side, and the negative current is basically, or the electron is flowing the other side from negative to a positive terminal. Like this it will move, electron will move like this, current will move like this. So, that means we are supplying electron to the metallic object. First thing is done. And second thing is making the metal object a cathode. Since we have connected this metal object to a negative terminal, we have made it cathode. So, cathodically protected because of cathodic reactions on the cathode surface. So, this is nothing but cathodic protection. Now, let us see what are the some of the points associated with cathodic protection. First point is, this method is widely used to protect steel structures or any structure such as pipeline buried in soil or immersed in water tank. So, protection to pipeline and that too immersed in water or what in water, then water tank like that, where you have intimate contact between the metallic object and the electrolyte. This intimate contact is essential to have a cathodic protection, to go for cathodic protection. And second thing is, this method is very, very useful if you have a barrier coating on that metal object. So, that case, let us say you have a barrier coating. So, many times it happens because of transportation and other things, some of the parts of the barrier coated part can be exposed. Let us say this is my metallic object and this is my barrier coating. Now, let us say this small part is exposed because of some damage. So, that damaged part will have a very good protection if we have a cathodic protection given to this system. So, it means that the coating, in presence of coating, this method is very useful. This is cathodic protection. Now, it can prevent both general corrosion or localized corrosion, let us say pitting or crevice. So, it can give impart protection towards general or localized. Protection to localized general or localized corrosion. Then, as I have mentioned, that intimate contact between the metal object which is under corrosion protection by cathodic means and the electrolyte, if you do not have that contact, then that part cannot be protected. So, that is to be taken into consideration. So, intimate contact is very important. And then there could be a problem of shielding. There could be a problem of shielding. Let us say the shielded region or let us say the inner member, example is inner member of in a bundle of inner member in a bundle of pipes. So, for example, you have let us say this is a bundle of pipe. So, this pipe is moving like this. So, this if you have a cathodic protection, then this inside part will not have any protection, because this inside part is getting shielded by the outside region, outside pipes. So, shielding, let us see what is actually shielding. Let us say we are going for a protection of water tank. We are going to have a protection of this water tank. This is electrolyte. Now, that protection is done from external power source, external DC power source. So, that means, if we would like to have this metallic object which is to be protected from corrosion, so we will connect this metallic object to the negative terminal of the power source. So, we will connect it to a negative terminal of the power source, and we will also have a inert auxiliary electrode. Positive terminal is connected to an inert auxiliary electrode. So, I have negative current is going through this, electron is going there, and the circuit is like this, the current is flowing like this, this is current, and that current is going all direction to all the parts of this metallic object, but here we have a pipeline. So, now in order to stop that water flowing out, we generally put a stopper, metallic stopper. Now, current is flowing all the direction and the external circuit is completed through this way. It will current will go like this and then flow back like this. But the thing is, when the electron is flowing like this, if we do not have this, electron can flow out like this, and it can have entire system together with this pipeline will be part of cathode, and then it can have a cathodic protection. But since we have put a metallic stopper, it means that we are basically short circuiting these two parts, and metallic stopper is giving a very less resistance for electron flow. So, instead of taking this path which has a higher resistance, this electron will take the least resistance path, which is nothing but the stopper. So, electron, instead of going like this, electron will flow like this. So, electron will come to this other section through this stopper. So, what happens? Wherever electron flows, that part will be cathode. Wherever electron does not flow, that part cannot be part of the cathode. So, now you see, initially if you do not have this stopper, metallic stopper, you can have the entire system under the cathodic protection. But once you have this stopper, this lower part, this part is not coming under cathodic protection. So, this part is basically getting shielded by this stopper. So, that is the entire mechanism of shielding. So, this shielding is basically trying to prevent that electron to flow out into this system, and this part will not be under cathodic protection. But initially the design, this power source is designed such a manner that the lower part is also will be protected, but actually we are not seeing any protection to the lower part, only this part is getting protected. So, the actual function what we have thought of having, that is not met. So, this is a case of shielding. Here also, if you have connected it to negative terminal, auxiliary electrode and in an electrolyte, so electron will flow from the outside section electron will flow, the inner part is not getting any benefit. So, inner part is basically getting shielded by the outside part. So, we have to take care of the shielding in order to have the proper protection due to cathodic mechanism, proper cathodic protection. Now, once we have this knowledge, let us see where we cannot use cathodic protection. Once this is known, we can easily consider those cases where cathodic protection cannot be employed. So, this is the sort of cathodic protection where we can apply cathodic protection, and now where we cannot apply cathodic protection. Cannot apply cathodic protection. So, once we have this general knowledge, then we can decide first is location above water line or the part which is not in under in electrolyte, which is not in contact with the electrolyte. So, that location above water line, because there we are losing intimate contact between electrolyte and the metallic object. Second thing is where we have non-conducting electrolyte, non-conducting liquid, not electrolyte, non-conducting oil or liquid. So, since here we cannot have any charge transfer reaction, because in this case the intimate thing is the circuit should complete, the current should come like this and flow out like this. So, we see that conducting oil or liquid, this cathodic protection cannot be applied. Now, one small point here, with respect to the first point, we have to have cathodic protection where we have intimate contact between the electrolyte and the metallic object, which is under protection. Now, if you see this picture, here we have connected this metallic object to the negative terminal. So, we have made it cathode, and this is auxiliary electrode is the anode. Now, you see the current is flowing through this external circuit and coming like this. Now, this is under protection. The another way to understand that which part of the metallic object is protected, we have to see that where the current is entering into the metallic object. Here the current is entering into the metallic object at this position, this position, this position. All the surface, outer surface is getting this current which is entering into the system. So, that external current we have to always see. Another way to see whether that part is protected or not, that is where which the part of that object, let us say this is a big object, this is a big object which is to be protected under cathodic protection. We have to see where the current is entering, external current. Now, we have to see that current is entering like this. Now, if current is entering throughout the outer surface, but not entering into this part. So, this part will not be under cathodic protection. So, this part can have still the corrosion can continue on this part, and the other part where the current is entering will be protected. So, this thing will come into picture when we will see that why we need to have a sort of enclosure by some metallic anodes to protect the metallic object. And so, this is to be taken care of. This is very important, because we have to see the main thing what we are trying to say, that we have to see that where the current enters into the metallic object, that part will be protected. If we have the screened area or shielded area, like in case of example where I have given in case of water tank with a pipeline attached to that water tank, the pipeline will be not under protection because of that shielding or because of that small metallic stopper what we are using, just to stop water flowing out through the pipeline. Now, the shielded part, we have to check the shielded part. If we have some part which is shielded, that section we should not go for any cathodic protection. And then fourth one is, though we are basically having cathodic protection to protect the object from corrosion, but if the corrosive media is very strong or extremely corrosive environment, we should not go for this cathodic protection, because that case cathodic protection will not be economically viable process or economically it will not be economically cheaper process. So, we have to go for something else. So, these are the 4 sections where we cannot go for any cathodic protection. We have to think of some different ways to protect those structures under these conditions. Now, let us come to the principle. Though we have talked about the principles, the principles are talked about in this section, but let us explain this part with respect to the mixed potential theory, since we know right now, by the time we know the mixed potential theory. Now, coming to again this E versus log I diagram, where let us say this is my I 0 for that metal and this is my I 0 for the cathodic reaction. Let us say the cathodic reaction is hydrogen evolution. So, we have to find out the new point where I see that the rate at which electrons are generated because of anodic reaction will be equal to the rate at which those electrons are getting consumed because of cathodic reaction happening on that metal surface. So, this is let us say M n plus plus n e, M going to M plus n e, and this is hydrogen plus E going to half H 2. So, this is cathodic polarization, this is anodic polarization. And we have also learned that cathodic polarization corresponds to I c and anodic polarization corresponds to I a. And at this point I a equal to I c with a negative sign, because these two currents are having opposite direction. Here this is I c direction and this is I a direction. So, that is what at this point the magnitude of these two current will be same with an opposite sign, and this is equal to I corrosion. So, I small I a is nothing but I corrosion at this point. Now we have said that we have to supply extra electron from external source. This extra electron can come from one external source or it can come from another anode material which is in connection with this metal object. But if we consider this case only, here we are having some external power source which is a DC source. So, there if we apply this negative current or the electron supply means nothing but the supply of negative current or the IC. See, if we increase the electron supply into this, so at this point we have equilibrium. So, this equilibrium will be broken, and since we are supplying electron to this, so we have more and more cathodic polarization. See, if we have more and more cathodic polarization, so this line will be extended. So, if we supply some extra electron, from this point it will have cathodic polarization. So, I will let us say after some time I am staying here. If I stay here because of this extra current flow, negative current flow or electron flow, so what would be the corresponding cathodic anodic polarization? So, we have seen that if we have this is my polarization over voltage and this is my log I with respect to a singular reaction, let us say this is N plus N E M. This reaction, if we consider this which is cathodic, so this is my cathodic reaction polarization line, which is nothing but this is I C, this is beta C log of I C by I 0, and corresponding if we consider the reverse polarization, it is my over voltage, anodic over voltage equal to beta A log of I A by I 0, and this is my 0 over voltage, and this is this corresponds to I 0. This is with respect to this, but here we have this and another different cathodic reaction. So, if I supply extra negative current, which is I C here, so then this polarization will move to the negative side. If I move to the negative side, what would be the corresponding polarization, anodic polarization? Let us say I am here. So, corresponding anodic polarization would be at this point. So, what would be my corresponding I A? Corresponding I A would be this one. See, if I stay here, my I A would be equal to I 0, but if I come here with a negative polarization because of negative I C, I see that I A is decreasing. If I A decreases, which means that I have much lower rate of this forward reaction. So, if I am here, so corresponding anodic current would be this one. So, if I do not do anything, the system will remain here, my corrosion rate will happen at this rate, at the rate equal to I corrosion. Now, if I take the polarization to the negative side, because since we are supplying extra electron to the system, so automatically I will go to the negative side. So, I will remain here after with respect to a certain amount of electron transfer, electron supply from the external source to the metallic object. My corresponding current density for the metal dissolution is this one. So, here I was, now because of this my current density for the anodic has reduced. So, if that means this is let us say I A dashed is less than I core, because this is in log scale. So, what does it mean? If this has reduced, the anodic current density is reduced, hence it is clear that my corrosion rate has reduced. So, this is the concept for cathodic protection. So, we have to take the polarization to the negative side. So, if I take the negative side polarization, because this is my reference point, now from this I went to negative, I am going to the negative direction, and correspondingly I am reducing the current density corresponding to the metallic metal dissolution reaction. Now, like that I can take it to this level. Further, I am reducing my corrosion current density or anodic current density. I can take it to this, but if you take it to this point and this point, what is the difference? Now, let me put some values here. Let us say this is my I 0. So, this corresponds let us say 10 to the power minus 10. Now, gradually if you reduce 10 to the minus 9, minus 8, minus 7, minus 6 minus 5 minus 4, and this let us say minus 4. IC is minus 10 to the minus 4, and here this is let us say 10 to the minus 9. So, what would be my applied current? Since we have seen that I applied is nothing but IC minus IA. I am putting a mod sign because we are just taking a difference between IC and IA, which is nothing but the I applied. So, as we go down, my I applied is increasing to a great extent, because if you, and then if I applied increases, what does it mean? I have to supply huge current to the system, and huge current means a lot of, it involves lot of money, because we are spending lot of power. Now, like this, so it is not advisable to go for a large cathodic protection, so that I can have also economic part should be looked after. So, that I can also have a reasonable money, spending money to the system, at the same time I will have a reasonable corrosion protection. So, that I can have a longer duration of operation with that metal part. Now, if you see that like that, if we go along this, if I can reach to this level, let me put it in red color, if I can reach to this level. So, if I supply IC to be, if IC is to be at this point, corresponding IA would be I0. So, corresponding with the red one, IA would be equal to I0. I0 is what? I0 is the current density corresponds to the non-corroding system. So, if I can reach here, I will get complete protection. So, if I can reach to the level of, if I can have this much, this much, this much, if I can reach to this much level of anodic cathodic polarization, I can take the cathodic anodic current density to this I0 level, and I will get complete protection. But this is again not advisable, because you see again I have to supply huge current to have the protection, complete protection. This is also not advisable, because it involves a lot of money, because we are supplying huge current. Now, if I can, if we can also go farther below. So, then what I am getting? If I reach there, so in fact that case I will have the reverse reaction, because this side is the cathodic polarization. But this is not advisable. There are, one reason is huge current supply, and second reason is, in case of amphoteric metal like zinc or aluminum, there will be further corrosion because of this, taking the potential below this. This is called cathodic corrosion. Cathodic corrosion, there is no surprise, because of making the metal in the cathode, since here is the cathodic reaction is going on, the reverse reaction will take place. So, since we are making it cathode, that time, because of this amphoteric nature of these two metals, complex ion can form in the system, either acidic or basic medium, and they can corrode instead of getting protection. So, that is why it is called cathodic corrosion. We will discuss it with the let us take it to the next level of discussion, and that too I will consider in the next class. Thank you.